Okay, this thought bubble here only works for geometric series. Okay, do not use that unless you have a geometric series. So let's write that down. These formulas. Okay, this a over 1 minus r business. Okay, this is for geometric series. So don't try to use it on a random series. Okay, so I repeat some things here that I've already said above, but worth repeating. Now let's go right into an example or two or three or four. First one. Pause and copy. Pause and copy. Beep, beep, bop, 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 beep. Okay, what do we got here? We got 2 over e plus 4 over e squared plus 8 over e cubed plus dot, dot, dot. So what you could do here is you could you can either take this expression and write it as 2 over e to the n, and then you see that we have a geometric series. Okay, we have an r to the power of n, and then the a in front is just a 1. Okay, now that you're convinced that you have a geometric series, you can go ahead and use your formula. So a is going to be first term, 2 over e, and r, I think the easiest way to find r is to take second term, divide by first term. And then I get 2 over e, which I probably already saw over here. Okay, now 2 over e is, in absolute value, less than 1. So I can use my sum formula. E is going to be a over 1 minus r, which is 2 over e. Ooh, 2 over e divided by 2 over e. It's just 1. Huh. Next one. I can rewrite this as e over 2n. So r is going to be e over 2, but that's bigger than 1. So series is divergent. Okay, this was the theorem above. It says a geometric series converges if and only if the r is between -1 and 1, strictly. Okay, about number 3 here. Where should I do that? So let's just go over here. Now I look at this big mess, and you could simplify. I want to put that as an exercise. Okay, write this as a sum from n equals 0 to infinity, a r n. Okay, so I want you to find a and find r, and write it like that if you can. Okay, just by manipulating this thing here. So it's worth trying. What I'm going to do instead is I'm going to go a is equal to the first term. So to find the first term, I take my first n value, so it's 0. So I plug n equals 0 into here. So 0 plus 2, 4 dot 4 to the negative 0. So we get 5 over 12 times 9 times 1, which is 15 over 4. 4? Yeah. And then I'll do r, which is second term divided by first term. So what's the second term? Well, you take this expression, you plug in 1. 5 over 12, negative 3 cubed, 4 to the negative 1, divided by 5 over 12 again, minus 3 squared, 4 to the negative 0. So I simplify that. What do I get? Say cancel, cancel. I get cancel, cancel. This is just 1. So what does that have me survive with? Negative 3 over 4. Negative 3 over 4. Okay. So now I'll say, well, this is between minus 1 and 1. So I can use my formula. So the original series, by which I mean this guy circled in blue up here, the original series, I just don't feel like writing it again, is equal to a over 1 minus r. And our a is 15 over 4. And then we have 1 minus negative 3 over 4, giving me 15 over 4 divided by 7 over 4, and we get the 15 over 7 that we want. Okay, for number 4 here, I leave this to you as an exercise. Try this. Here's the answer. You should get 3. So try that and ask me during class if you're stuck. So pause and copy. If you haven't done so already, maybe I'll shift down a bit. Pause and copy. Pause, 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 copy, copy, copy. Okay. Oh, this is fun. Rational numbers. I can take, pause and copy. So I can take this guy and I can write it as 0.12 plus 0.012 plus 0.0, oops, I forgot a 0. 0.0012 plus 0.000012, and so on. So I'm going to try to get a geometric series out of this. So this is 12 over 100 plus 12 over 10,000 plus 12 over, was that a million? Is that the next one? Sure. So that's 12 over 10 squared plus 12 over 10 to the 4 plus 12 over 10 to the 6 plus so on and so forth. So you should convince yourself this is a geometric series. How can you do that? Well, the feature of a geometric series that I should have underlined already is that if you take one term and you divide by the preceding term, you always get the same number. So you can try that for a few terms. You can say, okay, this divided by this is going to give me a number, and then this divided by this is going to give me a number, and do that 3 or 4 times, and you can convince yourself that I'm getting the same number every time, so this is a geometric series. Okay, we'll just skip that for now. The first term is 12 over 100. The R is second term divided by first term. 1 over 100. So therefore my repeating decimal is A over 1 minus R, 12 over 100, 1 minus 1 over 100, which is 12 over 100, 99 over 100. So you get 12 over 99. You may have seen this kind of trick previously in your education, but here is a more thorough demonstration. So what I mean is you may have seen that, okay, if I have 12 over 99, that's going to give me this decimal. And if I have 137 over 999, then I'll get 137 repeating, and blah, blah, blah. Okay, I want you to try the exercise, so pause, copy, try. And the answer is 1. So therefore, we conclude that there is no difference between this repeating decimal and the number 1. That may seem strange to you, but maybe think about subtracting 1 minus this decimal. The answer's got to be 0. Okay. A couple properties of convergence series. Okay, something we've seen before with integration. Okay, the constant multiple can move out front, so the C can move out front. And you can do this distribution. However, these are convergence series, okay? So don't try to play this game if you don't have convergence series. So the examples, first one, I can break this up. Like so. Now, the individual pieces here. Here I have a geometric piece that has an R equal to 1/3. And here I have R is equal to 2/3. Okay, so both of these numbers are between -1 and 1. So I can conclude that this distribution is valid. So I have 2 geometric series. So in both cases, I use A over 1 minus R. My series are starting at 1. So for this guy, the first term is 1/3, and the R is also 1/3. For this guy, the first term is 1/3, 2/3, and then the R is 2/3 as well. So sorting this out, plus 2/3 over 1/3 is half plus 2, which is 2.5, which is 5 over 2. Okay. For number 2 here, I have a problem. You can break it up and write it like this, right? Here you could think of it as R is equal to 1. Put in, artificially, you can put an n there and say R is equal to 1. So, summation 1 to the n is divergent. Okay, so I should not be distributing here. Instead, you argue that you have this is actually plus infinity. And then, the argument here is that you have a series that is plus infinity, and then you look at your original series and you say, well, that's actually more, right? It's actually in some sense bigger because you have this additional term here. So I'm not going to require you get too much into the arguments here. In this class, I'll let you just say something like this, or just say something like, okay, if I have a convergent part plus a divergent part, then overall it's divergent.